We start a new chapter on trees. I'll skip the agenda. So we first start with the discussion of graphs. A graph is a non-empty collection of vertices which are connected by edges. So look at this figure here. Here the blue circles are what we call the vertices, or also called the nodes. And these lines connecting the vertices are called the edges, or also called the arcs or the links. So, for example, consider a real map where we have cities and the roads that are connecting the cities. We will represent the cities with the vertices. So we have city A, city F, G, I, K, whatever, and the roads that are connecting these cities. Note that there are direct roads between some cities, like there is a direct road from city A to city F, but not from city A to city G. So a path defines the sequence of cities or vertices that should be visited to go from the source, say A, to the destination, say K. So to go from A to K, I can define a path like A, F, I, K, or an alternative path like A, B, G, J, K. Of course, you can find many alternatives in this graph. Graphs are quite useful in computer science. They're used, first of all, in all navigation systems like Google Maps, Yandex Navigator, TomTom, or any other navigator you find represents the map as a graph. Then you can easily talk about how you navigate in the city on that map. For example, in a navigator like Google Maps, the cities, the length of the road between city A and F, say, is 5 kilometers. Between F and G, say it is 2 kilometers here, 3 here, 2 here, 2 here, 1, 1, 4, 2, 2, let's say. Okay, you can fill the whole graph. Now, for example, if you ask Google Maps to find you the path from A to K, which has the lowest cost, where cost is defined as the length of the roads, then Google Maps will look at it. There are alternatives, like it could go as 5 here, 3 more, so it's 8, 10. An alternative could be 5 to 7, 9, 11, so that's words. 5, 2 makes 7, 8, 9. This is shorter than AFIK. Or another one could be 2, 4, 5, 6. This is even shorter. So assuming that the other ones, like, it's just very high values here to make them infeasible. The shortest path in this case would be, let me pick a different color, from A to B, B to G, G to J, and J to K. Okay, now this is in terms of distance, because all these values, as we made in the assumption, were defined in kilometers. If you just change the values here and make it, say, in terms of hours, which is the time it takes from to go from A to F, F to I, then you can find the best route, this time optimizing in terms of time rather than the length. So you can always change these parameters. It could be the length of the road, it could be the time to travel on that road, it could be the amount of gasoline you would be spending to go over that road, or if it's a toll road where you have to pay to drive on that road, then it could be the cost of driving there, the toll amount. It could be any parameter you wish. Anyways, as we said, the concept of graphs is a very important topic in computer science, but it requires more attention, and it's beyond the scope of this course. There are separate courses on graph theory, which takes one full semester, so we're not going to discuss graphs in more detail anymore. However, we are going to discuss in this chapter specifically a specific type of graph, which is called a tree. A tree is still a kind of graph, but it's limited. It's a connected and acyclic graph. Connected means between any two nodes in this tree, there is always a path. You might have to jump over several nodes, but there is always a way to go from any node to any other node in this graph. Therefore, this graph is connected. If you find any node that is not connected to some other nodes, not necessarily to all, but to some other nodes, then it would be a disconnected graph. That's not the case here. And the term acyclic means there are no cycles in this graph. A cycle is a path which starts and ends at the same node, but on the way, it does not visit any node more than once. Only the first and the last ones are visited twice. They're the same node. And the rest is visited only once. If you find such a path, it's a cycle. And therefore, the graph would be cyclic. But here, there are no cycles. For example, if I were to modify this graph by adding, say, a link between 4 and 17, now I would have a cycle like this. I start from 4 and come back to 4 by visiting no other node more than once, and I end up at the same node. Therefore, I have a cycle. Therefore, when you add the mentioned link to this graph here between 4 and 17, you create a cyclic graph. Therefore, it's not a tree anymore. But when you delete it, it's again a tree. So once again, a tree is an acyclic connected graph. Now, this also looks very similar to the real trees we see in our daily lives. Here, the node in brown, 18, is the root of the tree, and the nodes in green are the leaves of the tree, and the nodes in yellow are the intermediate nodes. Okay, so again, this is the root, and the green ones are the leaves. Well, this looks like a tree, but in computer science, we draw those trees upside down. So we put the root at the top, and the other nodes below. So the leaves are typically towards the bottom. So it's an upside down tree. And the reason we are drawing it this way is in any tree there's a single root. Here the root is 18. So I have a single point to start working. That's why we put the root at the top. So there are a couple of definitions we need to make about the trees. One is the parent-child relationship. Well, we're somewhat familiar with this concept because when we discussed the concept of class hierarchies, we already had the ideas of parent classes, child classes. So it's the same thing here. Actually, that class hierarchy was also a kind of a tree hierarchy. So 18 is the parent of 24 and 26, and we say 24 and 26. If you look at the other way around, we say 24 and 26 are the children of 18. The parent is also called the ancestor. So in reverse, we say 18 is the ancestor or the parent of 24. Parent is a more common term. And for the child, there's also the term descendant, but again, most of the time we use the term child. There's also the concept of leaf nodes, as we briefly discussed. A leaf node is a node that has no children. So if you look at this tree, the green ones are the leaf nodes because they have no children. 15 is not a leaf node because it has one child. And also note that 5 and 16 are at two different levels than the others. So the leaves are not typically always at the bottom. You could have leaves higher up in the hierarchy. The important thing is it should have no children. From here we also come to the concept of level. So level is the length of the path from a specific node to the root. For example, we say 24 is at level 1 because you need one hop to go to the root, which is 18. 23 is at level 2 because it requires 2 hops. 12 is in 3 hops, so it's in level 3. And 16 requires 1, 2, 3, 4 hops to go to the root. Therefore, 16 is at level 4. We also talk about the depth of the nodes. So the depth of a node is the distance between, again, that node and the root. Therefore, whatever your depth is, that's also your level value. So level and depth, in other words, are equivalent. Height is just the other way around. In the case of height, as opposed to depth, we're not looking towards the root, but in the case of height, we're looking towards the leaves. For example, if you consider 13, 13 requires one hop to go to the to one of its leaves, or this one, same. So the depth of the height of 13 would be 1. The height of 26 would be 2. So to any one of these 3 leaves, it requires 2 hops. If you look at 24, now 24 requires 1 hop to 5, but it requires 2 hops to 12, 7, and 4. And it requires 3 hops to 16. And we're looking at the longest possible path. So the longest one would be to 16. Therefore, we say 24 is at a height of 3 hops. Okay. Now we also talk about the height of the tree. The height of the tree is the height of the root. So in other words, the height of the tree is the longest path between the root and any leaf node. Among these leaf nodes, the furthest one is 16, which is 4 hops. Therefore, the height of the whole tree is equal to the height of the root, which is 4. To repeat once again, the depth is towards the root, the length of the path towards the root. The height is the length of the path towards the leaves, the longest one. Therefore, the root always has a depth of 0. It still doesn't have depth 1, depth 2, 3, so the depth is equal to level. Whereas in the case of height, that would be the difference between the level of the highest leaf and the node you're looking at. How do we represent such a structure? Not the graph, but the tree. How do you represent such a tree? Or the way we were looking at it was the upside down version. How we represent this in the program. One straightforward way would be you have a pointer to the child, actually to each children, but note that some children have more than one child. So 24 has 3 children, 23 has 2 children, 9 has 1 child, 5 has no children at all. So how do I manage the variable number of children? I could have even nodes that have more than 3. You could have a node which has, say, 10 children. So there's no limit on the number of children. So one way to solve it would be having such a data structure. We need one field to contain this value here, whatever it is. We're just, when we're drawing it, we're taking it simple. So we're here writing either some letters or numbers. But in fact, what you would have here would be full records, like all information about a student or all information about a course, whatever. So you could have a tree for anything. Therefore, let's make it an object. So this field is of type object so that we can write there anything. Now, for the other two fields, the first one is the pointer to the first child. But I could have variable number of children. Therefore, I don't have links to the second, third, whatever. Instead, everyone has a pointer to the next one. So you have a tree like this. A has children B, E, F. B has C and D. F has G. E has no children. You represent it with a graph like this. A has a pointer to its first child, B. B has the pointer to its siblings. Sibling means brother or sister. So B points to the next one, E. E points to the next one, F. So remember, B, E, F, they all have the same parent, therefore they're siblings. So to go to E, you should first go to the first child, and from there you jump to the next, you go this way. To go to D, for example, from A, you should go to first child, then sibling. So first child, then sibling. C, D are siblings, but they are not siblings with G, because the parent of G is F, which is different than B. Therefore, they are not the children of the same parent. So F has a pointer to G, which has no siblings. Therefore, its sibling pointer is null. We show it with an empty box here. F also has no sibling. That was the end of that list of siblings. So that's also null. Similar is true for D. C, D, and also E have no children, and also G. So for the first child link for C, D, E, and G is null. And also the parent has no sibling. Sorry, the root has no sibling. Remember, the root is the only one at that level. Therefore, its sibling field would be null. That's a possible representation, but definitely this is not a good representation. Like if I have a node with many children, you would always jump to the first, and then from that one you jump to the next. So if you have 10, for example, children, it would require 9 jumps, 9 unnecessary jumps to get at the last one. So this is not a very good representation. It's a quite awkward representation, but luckily in a few slides we'll be considering some better representation.